Hello students, today we are going to discuss some theory concepts of chapter system of particles and rotational motion. Okay, we are going to revise some theory concepts. So first of all, for system of particle, we will consider system of two particles. Okay, system of particles. Now particle 1, suppose both particles are on x-axis. This is the position of particle 1 and this is the position of particle 2. This is the origin, x is equal to 0. This distance is x1. So it is the x coordinate of particle 1 and x coordinate of the particle 2 is x2. Suppose center of mass of this system is somewhere here. Center of mass can be obtained by the concept of mass moment. Mass moment is the product of mass and perpendicular distance. Okay, and with respect to center of mass, the resultant mass moment of the system is 0. Okay, so suppose this is the center of mass. Position of the center of mass can be obtained by this formula. X coordinate of center of mass is m1 x1 plus m2 x2 upon m1 plus m. Okay, center of mass of the system of two particles can be obtained by this formula. Now suppose m1 is equal to m2. Okay, it is equal to m. So xcm is mx1 plus mx2 upon 2m. So it is x1 plus x2 by 2. What does it mean? For, for the system of particles, system of two particles having same mass, the center of mass is a midpoint. Center of mass is a midpoint. Okay. Now let's discuss one another case for the same system of two particles. Here we are going to derive the relation of the given total distance with the distance of particle 1 from center of mass, that is suppose r1, and distance of particle 2 from center of mass. So this is my system of two particles, particle 1, particle 2, and suppose this is center of mass. Distance between two particles is r. Distance of the particle 1 from center of mass is r1 and distance of particle 2 from center of mass is r2. Okay, so here you want to find r1 r2 in terms of r m1 m2. Normally suppose this is the case, you will be given mass of particle 1, mass of particle 2 and distance between them. Okay, for example, you are given that hydrochloric HCl molecule. So in that case, if you are asked to find center of mass of this system, okay, so in that question you will be given mass of hydrogen, mass of chlorine and distance between them. Okay, so mass of particle 1, mass of particle 2 and distance between them are generally given. Okay, so we have to find center of mass, distance of center of mass from particle 1, that is r1, and distance of particle 2 from center of mass, that is r2. So I consider that particle 1 is on origin. Suppose particle 1 is on origin, so its x coordinate is 0, and for particle 2 its x coordinate is r. Okay, now xcm, center of mass, position of center of mass m1 x1 plus m2 x2 upon m1 plus m. Okay, what is your x coordinate of center of mass? It is r1. Okay, xcm is r1 because x1 is 0, m1 x1 is 0, m2 x2 is r upon m1 plus m. So r1 is m2 upon m1 plus m2 r. Okay, so this is the distance of particle 1 from center of mass. Okay, r1 is the distance of particle 1 from center of mass. Similarly, if I find r2, it is m1 r upon m1 plus m. Clear? If I take ratio r1 by r2, r1 by r2 is, if I take ratio, so r will get cancelled, m1 plus m2 will get cancelled, so I will get m2 by m1. So r1 by r2 is equal to m2 by m1. What does it mean? R is inversely proportional to m. R is inversely proportional to m. Means center of mass is closer to heavier particle. Okay, so if you are given system of two particles and if you are asked that roughly where the center of mass should be, so it is always nearer to heavier particle. It is always nearer to heavier particle. Okay, if I consider the system of Earth and Sun, then I can conclude that center of mass of the system is nearer to Sun. This is very important, and it's about the center of mass of system of two particles. Clear? So if you are normally in any question, generally m1, m2 and r are given. m1, m2 and r are given. So you can directly from this formula calculate the distance of the particle from center of mass. Clear? Now this is, here we have discussed center of mass for system of two particles. Okay, suppose it is the system of n particles. Okay, system of n particles in either 2-dimension or 3-dimension. Okay, so position of the center of mass rcm is m1 r1 plus m r and so on mn rn upon m1 plus m2 and so on. Okay. Similarly, suppose I am given, for given system of particles, I am given velocity of particle 1, velocity of particle 2 and like that. Okay, then I can find the velocity of the center of mass. Velocity of the center of mass is, you have to replace r by v. Okay, m1 v1 plus m2 v2 and so on mn vn upon m1 plus m2 and so on. And similarly, if I have to find center of acceleration of the center of mass, the acceleration of the center of mass is m1 a1 plus m2 a2 and so on mn an upon m1 plus m2 and so on mn. Clear? Now consider this m1 plus m2. This is the total mass of the system. Okay, so can be written like this: mvcm. This is the total mass of the system. mvcm is m1 v1 plus m2 v2 and so on mn. Okay, m1 v1 is the moment of particle 1, m2 v2 moment of particle 2. Okay, so this is p1, that is the moment of particle 1. m2 v2 is p2, moment of particle 2. Similarly, mn vn is the moment of particle n. But mvcm cannot be written as pcm. Okay, pcm means moment of that particle which is center of mass. But in that case, it should be mass of that particle only. Here it is the mass of whole system. Okay, so m1 v1 is p1, m2 v2 is p2, mn vn is pn, but mvcm is not pcm. Here m is the mass of total system. But velocity, it is the velocity of that particle which acts as a center of mass. So mvcm p1 plus p2 and so on pn, that is p. Okay, so if I have to find total linear momentum of the system, what I need, mass of whole system but velocity of the center of mass only. Okay, so product of mass of the whole system and velocity of the center of mass gives me total linear momentum of the system. Okay, if I derivate this with respect to time, I get MACM equal to by, it is F. Okay, so it is the resultant mass on system of particles. It is resultant mass on system of particles. Clear? So again, if I have to find resultant force on system of particle, so what I need mass of the whole system, but acceleration of the center of mass. Okay, here F is the resultant external force. Okay, because we know that for system of particles, internal forces are equal in magnitude, opposite in direction, so they cancel out each other. Okay, so here when it is a system of particle, we will consider only external forces. Clear? We will consider only external forces. So this is the Newton's second law for system of particles. MACM is equal to dp by dt is equal to F is Newton's second law for system of particles. Clear? From here we can consider conservation of linear momentum. Okay, if I discuss conservation of linear momentum, suppose resultant force on the system of particle is 0. Suppose resultant force on system of particle is 0. Okay, then MACM 0, mass cannot be 0, means acceleration of the center of mass is 0. but acceleration of the center of mass can be written as d Vcm by d. So Vcm constant, velocity of the center of mass constant. This is important. The resultant force on the system of particle is zero. If the resultant force on system of particle is zero, in that case, acceleration of the center of mass zero, but velocity of the center of mass constant. Velocity of the center of mass constant. Okay. Suppose if the system, suppose I consider chemical bomb as my system, and suppose chemical bomb is in motion, okay, and suddenly it explodes into several fragments. In that case, different fragments will be thrown in different direction, but as far as center of mass of the system is concerned, the velocity of the center of mass is constant, because here there is no external force, linear momentum is conserved. Okay, so the center of mass will have the same velocity with which the bomb was moving. Okay, so after explosion, different fragments are thrown in different directions, so they have different momentum in different directions. But as far as center of mass is concerned, so velocity of the center of mass is the velocity of the bomb before explosion, because Vcm is constant. Okay, here you have to notice one thing: linear momentum of the system is conserved. Linear momentum of the system is conserved means linear momentum of the system constant. Okay, but the linear momentum of the system is the vector sum of linear momentum of each particle. Okay, here one has to note one thing, that total linear momentum of the system is constant, but it does not mean that linear momentum of each particle should remain constant. Linear momentum of each particle may change, but it should change in such a way that total linear momentum should remain constant. Okay, if I consider this room as my system of particles, okay, molecules are moving here and there. Okay, the whole system is in equilibrium, net force zero. Okay, so momentum, net momentum of the system is zero. Okay, but this part, the molecules which are moving here and there, they collide with another molecule or they collide with the wall. In this collision, their momentum change. Rare, but they change in such a way that resultant linear momentum remains constant. It is not necessary that for the system of particle that the linear momentum of each particle should also remain constant. It may change, rare, but it should change in a such a way that resultant moment of the resultant momentum of the system should remain constant. Okay, so there are ACM 0, VCM constant. These are 1 mark question. Now, here we have considered system of particles where particles are distributed discretely. Let's consider continuous distribution. Okay, so like it is, we are considering solid body. Now, if the system of the particle is in the form of solid body, in that case, we are not able to consider each and every particle individually. Here, what we will do, we will divide the system into small mass elements. And each mass element is so small that we can consider each mass element as a single particle. Okay, so in that case, for continuous distribution of particles, the center of mass RCM can be written as Cm1 R1 plus Cm2 R and so on, Cm and Rn upon total mass. Okay. Now the elements are very small and it is continuous distribution. So this summation will become integration. Okay. So RCM is integration RCM upon integration dm. Okay. This is for solid body. Okay. If I have to find only x coordinate of the center of mass, then it is integration x dm upon integration. If I have to find center of mass of y coordinate only, then integration y dm by integration. If I have to find z coordinate only of center of mass, integration z dm by okay. If the mass distribution is linear, okay, the mass distribution is linear, then dm can be written as lambda dm. Linear mass density into length will give you the mass of element. If it is surface distribution, the mass is uniformly distributed in surface, so it is sigma dx, where sigma is surface mass density, that is mass per unit area. Linear mass density is mass per unit length. And if it is volume distribution, if the mass is uniformly distributed in volume, then your dm is यहाँ पर एरिया. ठीक है. Clear? Suppose consider this thin rod. Okay, it is on x-axis. So here, because it is thin rod, I will consider that it is linear mass distribution. Okay. Suppose one end of the rod is at x is equal to 0. Length of the rod is L. X is equal to L. Okay. So mass is distributed along the length. So it is linear mass distribution. Suppose you are given that here for this linear mass distribution, linear density of mass is lambda naught x. Suppose lambda naught x square. We are asked to find center of mass of this rod. Okay. Mass is not here, mass is not uniformly distributed. Mass is not uniformly distributed. But one thing is sure, that the center of mass is there on x-axis. Complete mass distribution is there on x-axis. Definitely the center of mass is also on x-axis. Okay. So xcm, here we will go for this integration x dm upon integration. Okay. But we know that because it is linear mass distribution, is linear mass distribution, so dm is lambda dx, and your lambda is lambda naught x square d. Okay. So xcm integration x lambda not x square dx. First element is there at x is equal to, and last element is there at x is equal to L. So it is from 0 to L. Integration lambda not x square dx 0 to L. Lambda not. Now it is x cube, x square into x. It is x cube. Integration of x cube, x raised to 4 by 4. And in denominator, lambda not constant, integration of x square is x cube by 3. 0 to L, 0 to L. Lambda not cancel. So it is 3 by 4. L raised to 4 by L cube. So 3L by 4. Okay. So x is equal to 3L by 4, the position of center of mass for this. The mass distribution is uniform, and if the shape is regular, in that case, geometric center is center of mass normally. Okay, if I consider, suppose it is the object is square in shape and mass distribution is uniform. Okay, so in this case, the intersecting point of two diagonals, the center of that square, geometrical center of the square, same point is center of mass. If the mass distribution is uniform, if mass distribution is uniform, then geometrical center is center of mass. Okay, there are three types of center we can define: geometrical center, there are center of mass, center of gravity. Okay, if the mass distribution is uniform and shape is regular, in that case, geometrical center is center of mass. Okay, if the complete substance is in the same gravitational field, means gravitational acceleration g is same everywhere, then the center of mass is center of gravity. Because in that case, center of mass is the point with respect to which mass distribution is uniform. So if m is uniform in all directions with respect to center of mass, then mg will also uniform with respect to center of mass, and as a result, your resultant moment of mg will 0. So this point which is center of mass is also center of gravity. Normally it happens. Center of mass is center of gravity, because every normally whatever system we consider, it is always in the same gravitational field. Intensity of the gravitational field same. So he said, okay, तो अल्टीमेटली जहां पर मास का सेंटर है वहीं पर mg का सेंटर बनेगा. ओके, अगर ग्रेविटेशनल फील्ड इंटेंसिटी अलग अलग है, ओनली इन दैट केस center of mass and center of gravity will be different. Let me consider one hypothetical example. Suppose this is Earth and Moon. Now I have a rod, one end of this rod at Earth and one end of the rod is at moon. Now gravitational field of earth and gravitational field of moon are not same. Okay, suppose this rod is uniform. Okay, mass distribution in rod is uniform. If the mass distribution in rod is uniform, then the midpoint of the rod is its center of mass. Midpoint of the rod is its center of mass. But here, center of mass is not center of gravity. Okay, because near the earth, gravity G is greater. Near the in this side, near the moon, G is smaller. Okay, so in this case, because gravitational field is not uniform for this rod, the center of mass is not center of gravity. Okay, if the center of mass and center of gravity are not same point, what we can say about the center of gravity? In this case, it is nearer to earth. For example, center of mass, we have discussed that center of mass is nearer to particle, heavier particle. So similarly, center of gravity is nearer to the system which has greater gravity. Okay, if I consider this system, one thing we should note is that here, because gravitational field is not uniform throughout the length of the rod, the center of mass and center of gravity are not same. And another point, center of gravity in this case is definitely nearer to earth. Okay, so this discussion is about the center of yani system of particles. Now we will discuss about rotational motion. Okay, so in rotational motion, if I consider pure rotational motion, what happens when rigid body, and suppose the system of particle, I consider the system of particle rigid body. Okay, so if the rigid body rotates about any axis, you will notice one thing, that each and every particle of this rigid body performs circular motion. Okay, when rigid body rotates, it's each and every particle performs circular motion. Okay, and centers of this circular path are on certain axis. Centers of this circular path are on certain axis. This axis, this line called axis of rotation. This line is called, okay. Now angular displacement. Angular displacement. So suppose consider this rigid body. It rotates about the axis which is perpendicular to plane of board. Okay, and it rotates in this manner. So I have shown cross sections of this rigid body at time t and t plus delta. Consider x axis as a reference axis. Okay, as far as circular motion, as far as rotational motion is concerned, behavior of all particles similar. Okay, any one when body completes one rotation, each and every particle completes one revolution. Okay, so their angular displacement 2 pi. So as far as angular variables are concerned, they are theta, omega, alpha. Theta is angular displacement, omega is angular speed, and alpha is angular acceleration. They are identical for all particles. Yes, linear variables are not identical. Linear variables are not equal. Okay, r, that is for here, r is the distance from center. R distance from center are different, so velocity will be different. Okay, the magnitude of the velocity is 2 pi r by time period. because r are different. Distance from center are different for different particles. So their r are different, v, a are different. So for rotational motion, one should notice that linear variable are not same, but angular variable are same. Okay, r, v, a. R is the distance, r, v, velocity, and a, acceleration are different. But theta, omega, and alpha are same. Okay. So if I consider one particle, suppose at time t the particle is at point P, and at time t plus delta t the particle is at point P dash. Okay. So if I consider any representative particle on this rigid body, if I join this particle with its center, the angle between this line and your reference axis is your angular position. Okay, so theta is angular position of that representative particle, and the angular position of the representative particle is angular position of the whole rigid body. Okay, so for time t, at time t, the angular position is theta. If this angle is delta theta, then for time t plus delta t, angular position is theta plus delta theta. Change in angular position, change in angular position is called angular displacement. So your angular displacement is delta theta. For time interval delta t, your angular displacement is delta theta. Okay. Normally, angular position delta theta is measured in unit radian or rotation, and one rotation is pi radian. Okay. Now, if delta theta, please listen. If the delta theta is angular displacement in time interval delta t, then delta theta by delta t is your average angular speed. Delta theta by delta t is your average angular speed. Okay, if the speed is constant, if speed is constant, angular speed is constant, so omega can be represented as 2 pi by, okay, here I have considered time interval equal to periodic time, and we know that in time interval equal to periodic time, angular displacement is 2 pi. Okay, so if the rigid body performs uniform rotational motion, in that case angular speed is 2 pi by t. Clear? If I consider second needle of clock, so time period for second needle is 60 seconds. Okay, so its angular speed is 2 pi by 60, that is pi by 30 radian per second. Okay, then if I consider minute needle, so minute needle takes 1 hour, that is 3600 seconds for one complete rotation. So delta theta is 2 pi radian, but corresponding time interval delta t is 3600 seconds. That is pi by 1800 radian per second. Similarly, if I consider hour needle, then to complete one rotation, it takes 12 hours. Okay, so 12 into double, that is pi by 1600 radian per second. Okay. Similarly, if I consider angular speed of Earth about its geometrical axis, So it takes almost 24 hours. Okay, so 2 pi 24 into 600. It is pi by 43200 radian per second. Normally, angular speed is represented in unit RPM or RPS, rotation per minute or rotation per. This is rotation per minute. Rar. So 1 RPM. Okay, it is 1 rotation per minute. One rotation is 2 pi radian and 1 minute is 3 second. So it is pi by 30 radian per second. Similarly, if I represent omega in RPS, that is rotation or revolution per second, तो रोटेशन का पूरा रेडियन कितना होगा 2 पाई, डिनोमिनेटर में तो सेकंड ही है, इट इज 2 पाई रेडियन पर सेकंड. Normally, if you are given question, in given question, if omega is in RPM or RPS, and suppose theta is in radian, you have to convert this RPM or RPS into radian per second. Clear? Now, the direction of omega. If I have to find direction of omega, there are, I can be represented in many methods, but generally I explain it in this way. You have to consider screw, normal screw, keep it parallel to its axis, keep it parallel to its axis, and rotate the screw in the same manner in which the rigid body rotates. Then the direction of the displacement of the screw gives you direction of omega. So if it is anti-clockwise direction, direction of omega perpendicular to plane outside, and if it is clockwise, perpendicular to plane inside. Okay, but here we should notice one thing, that omega is either it is perpendicular to plane outside or perpendicular to plane inside, but it is parallel to axis. So omega is always parallel to axis. Okay, omega is always parallel to axis. Okay. Then what is the relation between linear velocity and angular velocity? Okay, so consider particle which is at point P at time t and P dash at time t plus delta t. Angular displacement is delta theta. This distance is r. Now, what is the linear speed, average linear speed of this particle for time interval delta t. So average speed is distance traveled by time taken. Average speed is distance traveled by time taken. Distance traveled is RPP dash upon time interval delta t. Arc is radius into angle subtended. Angle subtended is delta theta. So your average speed is R average omega. Average speed is R average omega. So for instantaneous relation, it is V is equal to R omega. Now, this is the relation for instantaneous linear speed and instantaneous angular speed. I want vector relation, means relation between linear velocity and angular velocity. Okay, so if I there are two possibilities, either V is R cross omega or it is omega cross R. Okay, so when omega cross the, if I find omega cross R, I will find that omega cross R is in the direction of V. Here, listen, this is the direction of R, this is the direction of omega, perpendicular to plane outside. Okay, and your linear velocity is in tangential direction. So if I represent both from same reference point, R and omega. Now, if I find R cross omega, okay, omega cross R. So I have to rotate screw omega cross R in clockwise direction, so it will move upward, which is the direction of V. But if I find omega cross R, sorry, R cross omega, so anti-clockwise the screw will move downward. So R omega cross, the direction of omega cross R and direction of V are same. So this is the linear vector relation. V is equal to omega cross R. V is equal to omega cross R is vector relation. Okay. Normally generally V is equal to R, we write V is equal to R omega, but that is for scalar relation. If if I want to represent vector relation, remember it is not R cross omega, it is omega cross R. R cross omega and omega cross R both are not in same direction. Both are in mutually opposite direction. Clear? Now I want relation between linear acceleration and angular acceleration, that is A and alpha. So I have to derivate this. So dv by dt omega as it is dr by dt plus d omega by dt cross r. Okay, dv by dt is your linear acceleration A. dv by dt is linear acceleration omega, dr by dt is linear velocity v, and d omega by dt is angular acceleration alpha. Okay, here it is very clear that omega cross v is also linear acceleration and alpha cross r is also linear acceleration. Means omega cross v and alpha cross r are component of linear acceleration, and component of the linear acceleration are linear acceleration. Now if I find omega cross v, direction of omega cross v, then I will find it is towards center, radial direction. It is towards center, so it is called radial acceleration or centripetal acceleration. The direction of omega cross v, the direction of omega cross v is towards center. Okay, so it is radial direction or centripetal direction. So this component of linear acceleration is called centripetal acceleration or radial acceleration. And this component of the acceleration is responsible for change in velocity. We know that acceleration, if acceleration is there, either due to this acceleration, magnitude of the velocity will change or the direction of velocity will change. Okay, but this component which is called radial acceleration or centripetal acceleration is responsible for change in velocity of the change in direction of the velocity. Velocity can be changed by either change in direction or change in magnitude or both. So radial acceleration or centripetal acceleration is responsible for change in direction of velocity. That is why we know that in circular motion there is only uniform circular motion. If I discuss, so in uniform circular motion there is centripetal acceleration only. And what happens in uniform circular motion? Only direction of velocity changes. Speed remains constant because only this component is present. Okay. So if I represent this component of acceleration in scalar form, normally omega magnitude of the omega cross v is omega v sine theta. But in circular motion, omega and v are mutually perpendicular. So theta is 90 sine 91. So it is omega v. But v is r omega. So it is omega square r or v square by r. Clear? Responsible for change in direction of velocity. Similarly, if I find direction of alpha cross r, if I find direction of alpha cross r, it is in the direction of tangent. Okay, omega cross v is along radius, alpha cross r is along tangent. So it is called tangential acceleration. Okay, it is tangential acceleration. This component of linear acceleration, this component of linear acceleration is responsible for change in magnitude of velocity. Okay, alpha r. Now listen, if your axis of rotation, if your axis of rotation is rigid, okay, is fixed, in that case alpha is also along axis of rotation. Okay, so alpha is also along axis of rotation, and so it is perpendicular to plane, and r is in the plane. So alpha and r are mutually perpendicular. Okay, if I consider rotational motion in which axis of rotation is fixed, okay, for example fan, the rotational motion of fan, in this case axis of rotation is fixed. So if the axis of rotation is fixed, in that case alpha is also along the axis of rotation. An axis of rotation is always perpendicular to the plane of the body in which it rotates. Okay, so alpha and r are mutually perpendicular. So sine theta 1 alpha r. Okay, and this component is responsible for change in magnitude of velocity. Magnitude of velocity. So this is the linear vector relation between v and omega. Okay, and this is the vector relation between linear acceleration and angular acceleration. Clear? Now, if I consider uniform rotational motion with uniform angular acceleration, जैसे हमने डिस्कस किया था यूनिफॉर्म एक्सेलरेटेड मोशन बराबर इन वन डायमेंशन, तो वही फॉर्मूला जो है उसको आपको क्या करना है, यू हैव टू कन्वर्ट इट, जस्ट आपको जो लीनियर वेरिएबल है उनको कन्वर्ट करना है रोटेशनल वेरिएबल में। ओके, तो ये जो रिलेशन था v इज इक्वल टू वी नॉट प्लस ए टी, ये क्या हो जाएगा, ओमेगा इज इक्वल टू ओमेगा नॉट प्लस अल्फा टी, फिर टी टी प्लस वी नॉट बाई टू इन टी, ये लीनियर डिस्प्लेसमेंट है तो यहाँ पर एंगुलर डिस्प्लेसमेंट आ जाएगा थीटा, या फिर आप थीटा माइनस थीटा नॉट भी ले सकते हो। मैं थीटा नॉट जीरो लेता हूँ तो थीटा इज इक्वल टू ओमेगा प्लस ओमेगा नॉट बाई टू टी, टी इज इक्वल टू वी नॉट टी प्लस हाफ ए टी स्क्वायर, ये हो जाएगा थीटा ओमेगा नॉट टी प्लस हाफ अल्फा टी स्क्वायर। फोर्थ, टू ए डी वी स्क्वायर माइनस वी नॉट स्क्वायर, ये क्या हो जाएगा, टू अल्फा थीटा ओमेगा स्क्वायर माइनस ओमेगा नॉट स्क्वायर। अगर आपको थीटा रेडियन के फॉर्म में नहीं दिया है क्वेश्चन में, सपोज थीटा इज गिवन इन टर्म्स ऑफ नंबर ऑफ रोटेशन, ओके, तो रिलेशन क्या होगा, थीटा इज इक्वल टू टू पाई एन, इस रिलेशन से आप एन को थीटा में कन्वर्ट कर सकते हो। एक रोटेशन, इफ एन इज वन थीटा इज टू पाई, फॉर एन रोटेशन इट इज टू पाई। तो नॉर्मली in case of rotational motion theta is not given directly in 2 pi in radian unit, it is normally given in terms of rotation, number of rotation, so you have to convert number of rotation into radian, then you can go for this. Okay,